Hello my friends, this is lecture 17, magnetic force. We're studying magnetic force now, and we'll talk about magnetic force on moving charges. This is highly used in research studying particles. They accelerate and send into a magnetic field. Depending on how they are curling around, we can decide their charges. Depending on how large the radius of curvature, we can decide their mass and so on. This is also how particles from the sun interacts with the Earth's magnetic field. If we have a charge stationary inside a magnetic field, nothing happens. If we have a charge moving parallel or anti-parallel, also holds. With respect to magnetic field, nothing happens. No force, no force. If we have a charge moving with an angle with background magnetic field, then we will have a force applied to that charge. It could be a large angle, small angle, or 90 degrees, which would give us a maximum force. And the force is always perpendicular to the plane of magnetic field and the particle's motion. To find the direction of that force, we will use a right-hand rule. There are two versions of that. One is this version here. FBI rule, FBB in this case. The middle finger shows the force to put them in a perpendicular fashion. Thumb shows the speed, and magnetic field is the finger in between them. I don't know the name for that finger. But I don't really use this. It's not always easy to apply. Unless you already learned about it, you're comfortable with it, I suggest not to use it. In many high schools, this is used quite often. I'm gonna use this version, curling hands version again, and in this case what we do is we set our arm and hand along the velocity first, then curl our fingers towards the magnetic field. So this is B, this is V, and open our thumb. Our thumb will be showing the direction of force. When we get the force applied to current carrying wires, we will apply the same approach, only current velocity will be replaced by current. So if I have a magnetic field speed in this fashion here, I put my arm and fingers along the magnetic field first, along the velocity first, sorry, and then roll them toward the magnetic field. So I have to rotate my arm to roll them, and then open my thumb. That will be showing the direction of the force. This is a quite bad drawing, but I hope you guys got the idea. So here's my hand. Here is how my fingers roll towards the magnetic field. My hand is along the speed. This is even worse than the previous one. And my thumb shows the direction of force. But this is the direction of force applied to positive charges. So positive charge force. For negative charges, it's the opposite. Here is it again shown for positive charges. So that's the idea. In this figure, in this question, we have this magnetic field lines are shown. At any point, magnetic field is tangent vector to those lines. So at the point of particle, we have magnetic field to the left. And I apply my right-hand rule, which I will call right-hand rule 3. I align my hand along the speed first. How to draw on really ugly hands, folks, bear with me here. And I curl my fingers towards the magnetic field. To do that, I'm gonna have to rotate my arm. I rotate and I curl. I'm gonna see that I have to curl them this fashion. As I do that curling, I open my thumb. That will show the direction of force, which would be out of the page in this case. For a positive charge, Negative charge would be the opposite. Again, this is my speed, my particle speed, and this is magnetic field. So force is out of the screen or out of the page. Similar questions might arise. There are some more examples we'll look at. How do we find that force? The magnitude of the force is this equation. The charge, magnitude of the charge. We don't worry about plus minus here because we find the direction using the right hand rule. Times the speed of the particle times magnetic field times sine alpha, alpha being the angle between the magnetic field and the speed. If alpha is 90 degrees, sine alpha is equal to sine 90, which is 1. So we will end up getting this equation. If we have perpendicular speed and magnetic field, we can go ahead and use this. And we will often have them perpendicular. Here I have a negative charge and its speed. The diagram shows the top view of an electron beam passing between the poles of a magnet. The beam will be deflected which direction? To the left, to the right, in, out. That's what we're looking for. I'm going to draw the magnetic field over here, north to south, remember. So what I'm going to do, apply my right hand rule 3, looking at this picture. I'm going to align my 4 fingers along the speed first, along the velocity. Then I'm going to rotate my arm to be able to rotate my fingers or roll my fingers towards the magnetic field. So I should do that. So always I roll my fingers towards the beam and put my hand along the speed first. Speed, nothing. As I do that and open my thumb, I will find the direction of the force. Let me use blue here. Quite ugly again, but hopefully gives us the idea. Force for a positive charge would be out of the page or out of the screen for a positive charge. Then I go ahead and say for a negative charge it's the opposite direction. It should be into the screen. So force is opposite for a negative charge. Or into the page for a negative charge, and we have a negative charge, so it should be into the plane. So here is the idea. I'm going to cross this out actually. This is a different approach, I notice now. Speed, magnetic field, negative charge. How do we do it again? Here's my arm. Here are my fingers. First a line along the velocity, then rotate my arm so I will be able to curl my fingers along the magnetic field. Imagine doing that with me. The force will be out for a positive charge. Open my thumb for a positive and in for a negative. Your phone actually measures the force applied to electrons inside a conductor to give you the direction of the magnetic field of the Earth. Isn't that neat? That's neat. That's neat. What happens to charges that are thrown into a wide area of magnetic field is that magnetic field keep applying a force perpendicular to their speed. Keep applying that force wherever I find, using right hand rule 3, I'll see that the force will be directed towards the center. And the particle thus will be making a uniform circular motion. Don't worry, we're not going to go into uniform circular motion alone in here. but just using the idea that the centripetal force equals to magnetic force here, because centripetal force is maintained by magnetic force. So we can find information about how large the circle is, the circular motion is, or its radius. If we know radius and some other values, we can find the charge and so on and so forth. So this equation here, what we will be using. If a particle goes into the magnetic field with an initial parallel speed, that parallel speed will drag it along the magnetic field. And the perpendicular one will cause it to rotate around the magnetic field. So we will have this type of a motion, the helical motion, which is what exactly particles from the sun does around the Earth's magnetic field. They rotate around, they rain down into the atmosphere, they collide with the particles in the atmosphere and cause beautiful displays, as we call auroras. This question is giving me the force and asking me which side is left, which side is north, which side is south for the magnets we have here. If it is in this fashion, my magnetic field would be in this direction, north to south, remember. If it's in the opposite fashion, it would be in this fashion. So either magnetic field to the right or left, and that will give me what is north, what is south. I have a positive charge and its speed is into the page. Imagine that. Now imagine with me, you put your arms into the page and put your hands, 4 fingers along the velocity in here. And then you want to roll your fingers in right or left. And as you do the rolling, your thumb should be up because the force is given up. As up. And if you do that, you will see that you have to be rotating your arm to roll your fingers to the left, so you will be able to have your thumb up. That means the magnetic field is to the left. That means we have this configuration. This side is north and this side is south. So as I complete this sentence, the magnet's north pole is on the right and the south pole is on the left. That is our answer, right, left. This one is asking what is the direction of the force on the electron. Here is the direction of my magnetic field towards the south pole, right? And the velocity anti-parallel. Remember, parallel or anti-parallel or not moving particles, there is no force. So force is 0, plus minus doesn't matter. I can also find it from here. The magnetic force is equal to Q V B sine alpha. Again, this is the absolute value, don't worry about the sign. If alpha is 0 degree or alpha is 180 degree, sine alpha is 0. Putting 0 here will give you overall 0. So mathematically as well, we can show that the force is 0 for a particle moving parallel or anti-parallel to the magnetic field. Another question here, imagine with me, and let's solve this together, which magnetic field causes the observed force. Force is out of screen, so my thumb should be out of screen. I put my hand along the velocity, 4 fingers along the velocity. Then I rotate my arm to curve my finger in a direction where the force will be out of the page. But keep in mind the right hand rule applies to positive charges. So I put my hand along the velocity curl my fingers in a fashion that thumb will be out of the page would be this. I curl my fingers. Okay, let me try to do a better job there. In this fashion. So if my force is that, my speed is this, velocity direction is this, magnetic field is that. Right hand rule. Make sure you imagine this, put your hand, arm along the velocity and apply it and convince yourself that this is right. But this is for a positive charge. Whatever I am finding, it will be opposite for a negative charge. So this should be my answer there. Look, what we found is for a positive charge. This would be my answer. This would be my magnetic field, choice A. But I have a negative charge here, so magnetic field should be opposite to that. My answer is C. This is a very, very interesting, important question. We have tilted magnetic field. Again, magnetic field should be that. I have electron with the speed, and the force applied to that electron is out of the page. Exactly inverse to what would be applied to a proton. In this case, though, they're asking us the direction of magnetic field. You find the direction of magnetic field for a proton or a positive charge, it will be inverse for a negative charge. Similar ideas here. Make sure you read and understand. We have an answer for this here. We have speed, positive, negative here. Which magnetic field allows the electron to pass through the charged electrodes without being deflected? We have electric field down, right? Electric field from plus to minus always. So if I am sending an electron in here, negative, electric field pushes it upward. Without even drawing the electric field, I would say positive would attract this guy. So the magnetic field should apply a force downward. Apply right hand rule, but keep in mind you have a negative charge to find the answer. It should be this answer. Convince yourself this is the right answer. Come and talk to me if you need to. A proton is shot straight at the center of a long straight wire carrying current into the screen. The proton will do which direction it will go? Into the screen. I'm going to apply here right hand rule 1. I'm going to grab my wire, 4 fingers along and curl, put my thumb into the page. Thumb into the page. It's hard to draw. And curl my fingers. They will be curling in this fashion. This will be the direction of magnetic field. As I go farther away, it decreases, but that's how it goes overall. Right? That's the fashion it goes. At exactly the point of the proton, as the proton comes in, this will be the magnetic field. I have magnetic field, I have speed, I can find the force applied to them. Now right hand rule 3, which is this approach over here. I put my 4 fingers along my velocity, then curl them towards the magnetic field. I rotate my arm to be able to do that depending on the configuration. Then my thumb will be showing the direct one. Thumb should be here, right? And it should be out of page. I have a positive charge here, so it should be pushed out. Let's check that again. Curve the finger upward. Put your arm and forefingers along the velocity first, then curve. You have to rotate and curve up. You'll have your thumb out of the page. Again, convince yourself that it's out of the page or out of the screen. Be pushed out of the screen is the answer here. We use our cyclotron machines to accelerate particles to a certain velocity, certain energy that we desire to make them do some work for us. The cyclotron does that. It's called cyclotron. So particle rotates in here and gets accelerated more and more and more. At some point it's shot out to a desired, reaching to a desired speed and desired kinetic energy. In this case, positron emission tomography uses this cyclotron to accelerate a particle, then fires it out, or proton actually, to oxygen atoms, and they create F-18. This is used for taking the tomography. For that to happen, we fire the particle in here, magnetic field curves it. We apply a potential difference, and the potential difference pushes it, gives it an acceleration that gives the larger radius. Why? Because if I look at my radius equation, rotational motion in my magnetic field, larger speed gives me a larger R. And then it goes around again. Here is pushed again by the potential difference, accelerated more, gets to a higher radius. It keeps going curving until again it reaches to a certain velocity, then it shot out and it does the work we wanted to do for us. This question is involving the cyclotron, medical cyclotron. It's kind of a plug and chug question, but there's an initial part. We wanted a proton to take a kinetic energy of 11 mega electron volt. That's 11 times 10 to 6 electron volt. And if it reaches that, it will be able to generate F-18 from O-18. If the magnetic field inside the cyclotron is 1.2 Tesla, so we know B, what is the radius of the proton's orbit just before it exits? So if I go back to the cyclotron here, just before it exists, the orbit is this guy in this case, and we're looking for this radius. We can use these equations to solve it, but what we have to find is the speed. And we find the speed using kinetic energy. So once we decide that, what we have to do is to calculate the kinetic energy in joules. I use all the SI units, remember. Input it in here and solve for the speed, which will be 5.59 10 to 7 meters per second. And then we will find the radius using that. There's also electromagnetic flow meters that are used to separate charges. So as the blood flow, there are charges inside it, positive and negative. If we apply a magnetic field in this fashion, for example, magnetic field is down, speed is to the right. If I put my hands along the speed, curve my fingers down, let me try to draw that. My thumb in this case would be going into the page, and the force would be into the page for positive charges, and it would be out of the page for negative charges. So this separates positive and negative charges. The faster the charges flow, the larger the force will be, because of this equation that gives us how the flow is. Is it fast, slow, is there any clogging, and so on. It's a very neat application as well. Alright, that's all for this. This one part is about trying it yourself, although it might not be a good idea. You might permanently damage your TV screen, but electrons are taking part in making our televisions work. So if you put a strong magnet beside it on the screen, would be a very good idea as well. The trajectories will be altered, so you will be seeing smudged images there. It might come back. Today's televisions are made better, but it might not come back and might have permanent smeared part on your television. But it's neat. It's something we can try if we have an old television. Alright, see you in the next lecture.